Hello again, folks, in 113. Today we'll be covering section 11.1, which will be the beginning of chapter 11 for us. And we're in the home stretch now. Okay, today is Thursday, November 18th, so as per the schedule, we're going to be covering 11.1. Okay, now the packet that I have for you consists of quite a few pages. I'm going to start with this empty diagram again for collecting terminology and some abbreviations, just a few. Then there are some overview diagrams I've made, probability games. Then there are two different formulas really that you need to take into consideration depending upon whether you're dealing with theoretical or experimental probability. Go through that with you. This is something I swiped from your book, which is helpful when discussing the differences in results. And also at the bottom, this is very important, the law of large numbers. Okay. Then there is a page I compiled of facts about probability. It's going to be important when we get into section 11.2 for the sake of contrast. Then this is an example that I took from another book, but I like it a lot because a lot of times this coincides with Halloween, so it's about candy. And then there are the actual examples from the book with the solutions. So you could follow along independently or with me. I included some of the textual, factual information from the book. I tried to make it as concise as possible, but the history of probability as a subject of mathematics is interesting. These will be the same formulas and definitions, but if you prefer, this is swiped from the textbook. And then there is a section on basic genetics, right, which is something that you could apply probability to. And I made a diagram to that effect. All right, so if you're following along to print this out, and we'll go through it slowly but surely. Let me adjust the device here. Doesn't look like it's quite in the frame, so that's a little bit better. Let me just scoop this over the other way. It'd be great if I didn't have to move this every day, but hey, it is what it is. Alright, let me just start with this as a background. Bootleg paint, there we go. Okay, now this is sort of not something worthy of an actual handout, but it's to give you an idea as to where we're headed this weekend until the middle of December. Right. We're in chapter 11, as I mentioned, is the home stretch. This is the last chapter for the semester. All right. When you begin in Mat 114, presumably in the spring, you're going to start with chapter 4, I believe. Anyhow, this is it for us, and there's 6 sections. So over the course of the next 3 or 4 weeks, we'll be covering this stuff. Today, it's just section 11.1. All right. What will be happening is we're going to compare probability, what we discussed today, to something called odds. They're not exactly the same thing. They're similar, and they're related, but they aren't the same thing. Then there's essentially a formula called expected value. a diagram, a tool known as tree diagrams for calculating, and different formulas for compound probability or conditional probability. Right? We have to get the essence of the subject, its definitions, its terminology, and its basic formulas down pat today. So we'll do that. Alright, now with that in mind, let's get through the terminology. Minimize that. And I'll erase this. Looks like it's reasonably sized. Okay. Let's start with this. The concept of an experiment, maybe a bit larger would be nicer. Yeah, that's good. Okay. Know these words: experiment, in contrast with this concept of outcomes. And events. And actual probability. Okay. An experiment in the context, usage of probability. An experiment is basically a game. We don't think of games as being experiments, we think of experiments as being something much more serious, right? But a very simple game that conforms to, a set of rules, all right, can be a basic probability experiment, and you'll see momentarily. As a matter of fact, I have some toys which I should dig up for when the time comes. Put that there. Handy thing. Basically, it is a game, or you might say a controlled operation that yields a set of results. Now, how does the word outcome come into play here? I'm hoping that this green is visible, and if not, I'll try some other color, but it's always these four. An outcome is one of the possible, I'll take the plural out of this, outcomes are the possible results previously talked about. Of an experiment. / game. Alright. If you think about it in a more, for lack of a better phrase, mathy sense, alright, it's the set of elements. Literally the set of elements. An outcome, one of them. Right? All outcomes in consideration are all of the possible results, therefore you might write them in set notation, in roster form. As for events, we finally get to something that employs an abbreviation. Right? A lot of times an event, as part of a formula, is abbreviated by the letter E. and in theory is any subset of the outcomes. Now, why it's good to remember set theory from earlier in the semester, you remember that a subset could include the entirety of all possibilities, all right? Or it could be something that is a proper subset, which would be, you know, something that is distinct from the original, the whole, all right? So it's any subset, right, of the outcomes. Could be everything, nothing, or a chunk. Of the whole, but not the whole itself. Right? That would be everything. Right? Could be the whole thing, nothing, or just a portion. Perhaps that would be a better phrase than chunk. A portion of the whole. Lastly, there's probability itself. All right. Probability is often abbreviated with a capital P, and then in the style of a function, so you'd see something that has parentheses. So if we're talking about a specific event, then you'd say the probability of the event. You'd insert this inside the parentheses. That doesn't mean you have to do something to it. You're not multiplying or anything like that, even if it sort of looks like that. Right? It's just a signifier, you know, an abbreviation, if you will. You'd read it literally as the probability of event such and such. Okay? And this is basically a number used to describe the likelihood of an event. Happening or occurring. 2 C's, 2 R's. Just to reiterate, the probability is making a number for the sake of comfort, believe it or not, a number used to describe the likelihood of an event occurring. Right? Basically, it's a fraction. All right, so know these terms. Experiments are games, really. Outcomes are the possible results. Events are any subset of the total outcomes. And probability is a number used to describe the likelihood of something happening. Now, what does this look like? Here are some diagrams to illustrate the actual games. So I'll just minimize that for a moment. See if I got all my stuff ready good. Let me get rid of this. If you wonder why is it that sometimes I give you diagrams and other times I sort of try to get you to write stuff, the basic reason for trying to get you to write stuff is that, especially vocabulary, which is the foundational information, if you write something, you're more likely to grasp it. Right? Even if you don't feel warm and fuzzy about it to begin with, in the long run, you're doing yourself a service by actually physically writing something rather than typing. Anyhow, take a look at this while I straighten my tie here. There are 3 basic probability experiments, i.e. games. Right? There's what you might describe as a coin flip, a die roll, or a card draw. And sort of to reinforce the idea, what I have here are some exaggerated examples of each. Here's an example of a coin. I found this when I first purchased my car. This was in my car. I don't even know what it is. It's sort of the lid did something. Anyhow, it happens to make for a very large coin, as long as you label it as such. So to make it more obvious, I put a red T on here for tails and a yellow H on the top for heads, right? And there's not much to it. It's the most basic probability experiment in the world, without smacking myself. Alright, to flip it, you either would actually get heads or tails, right? Unless it's a rigged coin, and it's not, alright? Anyhow, in consideration of the number of outcomes, there are two. Right. A coin flip being, it has two sides, and we're not taking the edge into consideration, really. You're either going to have heads or you're going to have tails. So in the style of set notations or set theory, you might put it in fancy braces and label it either just H, comma, T, or write out the word heads, comma, tails. Those are the two possibilities, right? Two possible outcomes. All right. When it comes to a die roll, at least if it's not something like a Dungeons and Dragons style die, if it's just a standard cube and not dodecahedron or anything, then the possibilities are a little bit more greater, right? There'll be 6 possible unique outcomes on a die, right? An individual die. And again, if you're going to write that in the style of a set, it would be 1, 2, 3, 4, 5, 6. Finite, thankfully, right? And the best you do is you just, sort of, roll it, right? All right, I made this out of some styrofoam packaging I got in the mail. And here's the second one, yay. All right, I should make these as dice and hang them from my mirror. Anyway, when it comes to a card draw, though, all right, a full-size deck, a regular sort of polka deck of cards would be 52 unique outcomes. Now, it's a little bit harder for me to list them here on my overview, so I cheated, all right? I used the ellipses to indicate that there's a slew of unique options in between the Ace of Hearts and, say, the King of Hearts, all right? And similarly, Ace of Spades to the King of Spades, Ace of Diamonds to the King of Diamonds, Ace of Clubs to the King of Clubs. Don't make the mistake that I have made, which is in the position of teacher, I have assumed that virtually anyone, especially a person who is of college age, has somehow or some way in their life played with a deck of cards. Don't make that assumption. When you discuss this with your students, your own students, bring them decks of cards, all right? They may have no clue, what the suits are, namely the hearts, spades, diamonds, or clubs, or that they're labeled with some pictures, all right? Not the most attractive people, right? Kind of pasty. And they're labeled with numbers, all right? Each suit goes from at least ace, which is regarded as either a 1, or in the case of, thinking of the game, blackjack is the equivalent of 11, but basically it's the number 1, all right? And the things that follow it in numerical order go up to 10, and then there are picture cards, which means that this is an 11, technically, a 12, and a 13, all right? Why am I bothering you with this? Well, because that means that there's 13 options here, and there's 13 unique cards here, and 13 of these, and 13 of these, right? Hence, 52 unique outcomes. All right, just bear that in mind. And again, don't assume that anybody knows what you're talking about, even though it's a game. All right? I used to live with my grandparents, so you could chalk that up to being sort of a Depression era sort of pastime, right? Or the activities of old people, aside from shooting dice, all right, and flipping coins. But I always took it for granted that every kid had ever played those games. Anyhow, we are going to assume, right, that the coins are not rigged, that the dies are not rigged, and that the cards are not rigged, right, when we do our homework or, do something theoretical. right? So yeah, coin has an edge, but we're considering it mathematically flat, meaning non-existent, really, right? And it's not weighted in any way, or there aren't extra cards. All right. Now, one thing you're going to notice, and maybe I should tell you this now, is there are two different types of probability. Let me show you that first. Which means that there's going to be essentially two different formulas, right? There's something called theoretical probability, and then there's empirical or actual experimental probability, right? That sounds maybe more important than it is. Not that it is unimportant, but it sounds more complicated than it is, right? Theoretical probability is more abstract, shall we say, so in your mind. And experimental probability is actually concrete. It's something that happens, all right? Actual experiments, right? You use theoretical probability when all outcomes you know are equally likely, right? No rigged dice, no rigged coins, no rigged deck of cards. Okay? Experimental probability tends to be useful when theoretical probability is not available, all right? Say you're talking about something more complicated than those three simple games, all right? Actual science experiments, right? Or if you're an insurance company, mortality rates, right? You know, it would be difficult to calculate a mortality rate abstractly. You use what is the actual available data, okay? As you're going around. You're not actually killing people, don't worry. The insurance company would not like that. All right. Now, insofar as the actual math is concerned, the actual numbers involved, so that makes it a little bit easy to see. These are the formulae, all right? Probability of an event, all right, is written in the style of a fraction. That's important, all right? Notice that this is something that appears in the style of a fraction, meaning that there is an obvious top and an obvious bottom and this line in between, all right? Right. What you put above the line in the formula is the number of outcomes favorable to the event, things that would benefit that happening, whatever situation that is being described. We're going to do some examples shortly. What you put on the bottom is the total possible outcomes in the sample space. All right. So essentially, the number of all outcomes, right, versus on top here, outcomes favorable to the specific event. The top is very specific, the bottom is more general. If that helps. Okay. Essentially the same thing, all right, when you're dealing with experimental or empirical probability. The label for the quasi-function here, P of E, doesn't change. The abbreviation is the same. However, the labels of what the top and the bottom are different. All right. Since it's based upon actually things that occur, observation, the label on top is known as frequency. Right. This is the actual number of times that something happens. Right. not just what theoretically would be favorable. Right? And the bottom number is the total number of trials of the experiment. So the total number of actual coin flips, the total number of die rolls, the total number of card draws. Right, in theory, right, well, experimentally. Right. The number of trials versus the actual occurrence. Right. Remember, when you see P parentheses E, sorry for the gobbledygook, let me get this out of the way. P of E, which is written here, right, and also here, right, is read as the probability of event E, whatever is specified in the problem or whatever is under consideration. All right, so just realize it is going to essentially be the same thing, a fraction that you're going to produce or that you will read, all right, but gleaned from doing something abstractly or concretely. All right. Now to complete this other thought, it was on the other page, but I'll flip back to it now. What you're going to notice eventually is that even in spite of talking about the same subject, the same coin flip, the same die roll, the same card draw experiments, empirical probability does not always equal theoretical probability. One would expect perhaps that they should be, right? But they don't immediately anyhow. Why doesn't empirical probability always equal theoretical probability? That is, why is it that you see empirical results that differ from the theory? Right? Because of something known as the law of large numbers. Right? Now, not to bore you, but let me read this. All right? In practice, probability applies to a very large number of games, right? And not just one or even a few trials. Meaning that empirical probability will approach the value predicted by the theoretical probability over the long run. Okay? So you will in fact see that these things are basically the same, but you would have to do enough experiments to actually see that. All right? You would have to have a large number of actual trials. Okay? Do bear that in mind. All right? So to get your feet wet, let's do some examples. I'll come back to this. I'm going to skip to example 3 because it's interesting and do some of them with you. Hopefully that is in the frame. This is fairly clear. I'm going to give you a little bit more light. I'm fighting the sun always. Alright. And take a sip of water here. Let me divvy up the board here. There are basically 1, 2, 3, 4, 5 parts to this. So I'll just start by cutting this into 3. Maybe I could fit more. I don't know what the heck that's in. Oh, it's the edge. Okay. So here's part A, B, and C. I'll move my mouse. Okay, now what are you asked to do? determine the theoretical probability. So we want to use basically this formula. The probability of event E is equal to the number of events favorable to event E over the total number of events in the space. Right? That's a little bit too ruined by the projection, so I'll write it like that. All right. Okay. We could have visual aids, right? But we're talking about a fair die roll here. One assumes a 6-sided die, right? And it's fair, it's not rigged in any way. Determine the probability of rolling a 2 specifically. If you were going to translate that, I'm sorry it's a little bit hard to see. If you were going to translate that, the probability of rolling A2 into the formula, you might write it like this, right? If that's the generalization, probability of event, you would write the probability, parentheses 2, right, would be a concisely written expression, right, is equal to the number of events favorable to 2 over the number of events in the sample space, right? I'm going to leave that as an S for a moment. All right. All right. How many sides of a 6-sided die are there? All right. Because we're talking about theoretical probability, the number that would sit here naturally would be 6. All right. All right. And, all right, the number of sides, events favorable to rolling a 2 would be how many? How many, although I know this is cheesy because I drew it myself, but how many of these unique sides actually have 2 dots on them? All right, it would be just 1, all right? What gets people bogged down, I think, sometimes is if you're talking about numbers, the number of numbers, it can get a little confusing. Kind of meta, isn't it? The number of events favorable to 2 to 2, that's what you would read in this, is just one of them. Right? So in a simplified fraction, all right, what would be the probability of rolling a 2? Essentially, the probability would be 1/6. 1 out of 6, you would say. Okay? You could, in theory, translate that to a percentage, but don't worry about that just yet. Right? B, right? Determine the probability of rolling an even number. Right? If I'm going to take that and adapt it to the formula, then I might write this as such. The probability of an even, right, P of even, is equal to the number of events favorable to rolling an even over the number in the sample space, so the space, just like in the set. Same difference. All right. Again, we're still talking about a 6-sided fair die. Right? So the number down here would be 6. Right? The number of events that are favorable to an even, though, would be different, right? This might be helpful if you actually see the possible sides written out for a moment. I'm not going to put commas, even though I should. All right? Of these things, 1, 2, 3, 4, 5, 6 of them total, that would be the numbers sitting here. All right, how many are actually even numbers? All right. Well, 2 is an even number, 4 is an even number, and 6 itself is an even number. So the figure that would sit here, number of events favorable to rolling an even, is not just one thing, it's several things. So what would be the figure? 3, right? meaning that the fraction in this instance would be 3 out of 6. Right. You should, and as a good habit, simplify. So what is 3 out of 6 simplified as a fraction? 1/2. Again, it might be a little bit more intuitive at this point to translate that into a percentage, which is totally cool when you're talking about probability. People tend to like hearing a percentage. We understand it easily, right? What's a half in the style of a percentage? There's a 50% chance of something of rolling one die and landing on an even. Okay? All right. So progressively more challenging. Calculate or determine the theoretical probability of rolling a number greater than 3. Again, if you're going to adapt that to in the context of theoretical probability formula, the probability in a very concise way of referring to this on number greater than 3, I'm going to use n to represent a number. And I'm going to use the inequality symbol that is greater than, all right, to illustrate that I mean a number greater than, bigger, all right, than 3. That may not seem like it's too important, but if you take the time to figure out what an appropriate abbreviation would be, all right, in other words, if you simplify the verbal gobbledygook into something more symbolic and concise, you probably will understand it more. All right, take that time. Now you could write this as the number of events favorable to numbers greater than 3 over the total number in the space, or the set. Okay? What is this number going to continue to be here? Well, we're talking about a 6-sided die. We didn't change the game, so it's still 6. There are 6 possible outcomes, right, in the set. Right. It again might be more practical, right, to write it out, the possible outcomes in set notation. So I'm going to write that 1, 2, 3, 4, 5, 6. All right. And now consider the things that are greater than 3. Which of these are greater than 3? Basically everything forward. So 4, 5, and 6 itself. All right. Coincidentally, then, how many outcomes are favorable to rolling something greater than 3? Right? 3 itself, right? 3 again, I should say, because we had that for the instance of even. So once again, it's 3 out of 6, which is a half, which is, if you like, a 50% chance. A fraction is sufficient. When you get more comfortable, yeah, go ahead and change it to a percentage. If you're curious about 1/6, it would be 1 divided by 6 and then multiplied by 100. Remember to convert it to a percentage. So it'd be something like, I think, 17%. .6 repeating, rounded. Right? The fractions are fine. All right. All right. Because I need the space, I'm going to erase a bit. And we'll do the last 2. And then we'll sort of shift gears here. Okay. Now we're going to calculate the probability of rolling a 7. Again, to adapt this to the formula, P parentheses with a 7 written on the inside. The probability of 7 would be equal to the number of events favorable to rolling a 7. And this is sort of like cardinality, remember, from set theory. The number of events favorable to 7 over the number in the sample space or the set. All right. This is still going to be a 6. All right. But without having to duplicate the actual roster here, how many sides of a 6-sided die actually are labeled 7? It's kind of a trick question, right? There aren't any, right? Unless you're dealing with a Dungeons and Dragons die or something like that. there aren't any. So the number of events favorable to rolling a 7 is actually 0, which means that the fraction would be 0 out of 6, or you could say 0%. Okay? It is absolutely not going to happen. All right. Last one here. The probability of rolling a number less than 7. So, probability of a number less than 7 is equal to the number of events favorable to rolling less than 7 over the number in the samples, or the set. Okay. This is still 6. And again, if you consider the things in the roster that are actually less than 7, they're all less than 7. All right? So this figure on top would coincidentally be a 6. All right? That means that your fraction is 6 out of 6, or you could say 1 out of 1 simplified, or just simply 100%. It is a certitude. It is absolutely certain that you're going to roll something less than 7. 100% chance versus a 0% chance of rolling an actual 7 itself. Okay? Alright, let me go back and do 1 and 2 now. And I'm going to compare theoretical and experimental later. Okay. Just make sure my camera still works. Take a sip of water. Okay. Example 1, to go backwards, would be in 100 tosses of a fair coin. All right, 44 heads, 44 landed heads up. All right, determine the empirical probability of a coin landing heads up. All right. Now remember, the formula for empirical probability is essentially the same thing. It's a fraction, meaning it has a top and a bottom, but the labels are intentionally different. So the very top is just an F, and the bottom is N. All right. So this is empirical or experimental probability. Remember that the bottom is the number of trials, games, etc. The actual number of times you've attempted this experiment, and the top is the frequency that actually occur. All right, never mind what the theory predicts. All right. So they're just describing something as being 100 tosses of a fair coin. Here again is a very simple coin, heads and tails, and those are the only two possibilities, remember. All right, we're ignoring the fact that it actually is a real object that has an edge. All right, so how many trials are there? All right, they don't use the word trials, right? But nonetheless, it's described as being 100 tosses of a fair coin. All right, which means that down here the number would be 100. If I want to write this, I'll put it over here in the context of this problem. The probability is equal to F over N probability of heads observed would be 100 down here. And then the actual frequency described is that it lands heads 44 times. So it's just 44 over 100. Being that it is already out of 100 trials, you could convert this to a percentage rather easily. It means that essentially this occurred 44% of the time. Alright. If you wanted to, you could simplify the fraction as well if that is preferred. Just take advantage of either using your calculator or rules of divisibility. Ideally, bless you, if you have GCFs. That's my sister sneezing. At no extra cost. All right. Special effects are great here, right? These are both divisible by 4. So this is overkill, but if you wanted to put this in a simplified fraction, it would be 11 over 25. 44% is probably more conducive, right? But that is the actual fraction, simplified. Okay? Alright, moving on. Let's look at 2. Oh boy. Okay. This is going to be, I believe, another instance of empirical probability. It's not just for the reason that we're talking about pharmaceuticals here. Let's take a look at this. A pharmaceutical company is testing a drug that is supposed to help reduce high blood pressure. The drug is given to 500 individuals. This number is going to be important. All right, with the following outcomes. All right, blood pressure reduced, 379 people. All right, blood pressure unchanged, 62 people. All right, blood pressure increased, 59. That's ironic, right? You give you this medication, it causes your blood pressure to go up. All right, that's terrible. Anyhow, if this drug is given to an individual, determine the empirical probability that the person's blood pressure is A, reduced, B, unchanged, C, increased. All right. Without whipping out the t-square again, let me just chop this up into those 3 questions. This is A, B, and then C. Okay. Here's our formula for empirical probability. The probability is equal to frequency over the number of actual trials. All right. So just to adapt it slightly, reduced would be equal to the frequency over the number of trials. All right. Unchanged same formula, frequency over the number of trials. Increased. Frequency over the number of trials. Not sure who that is, so let me just check. It's probably the male. Sorry. some stuff from my nephew. Sorry for the interruption. But nicely, it came on time. Very good. All right, now to get back to work here, as it were. All right, the probability of people reduced, just taking the information from here, the frequency of people that had reduced blood pressure would be 379 out of a total of 500 people, right, which we could reduce. All right. You could try to whittle that down. I'm going to cheat in this instance. All right, we're not reinventing the wheel, so what I'll do is I'll show you. You could take your calculator and have it simplify this fraction for you. If you enter it into your calculator, it automatically does that. So turn it on, enter the top number, 379, and then there is this button here, ABC, which, although it is a little odd looking on screen, that represents the fraction bar, sort of backwards L, right? And then you just enter 500. If it is in fact simplifiable, reducible, what you would see once you hit equals is the reduced fraction here. It is already in simplest form, okay? So that's cool to have that. So there you have it, 379, 5 out of 500, or 500ths if you like. If you feel more comfortable, explaining this to another person, remember you could convert this to a decimal and then convert that to a percentage. Where is that button? If you just take 379 and actually do the division, you're going to get the decimal equivalent, which would be 0.758, right? So in the style, I know I didn't ask you this specifically, but 0.758 converted to a pure decimal is the same as multiplying by 100, right? So the decimal place over, it would be 75.8% have blood pressure reduced, which is pretty good, about 76%. Okay. Unchanged would be 62 people, right? Out of the same figure, because it was 500 trials, right? And that's definitely something that can be reduced, right? Just because I have a sickness and I can't help myself, I'm going to try to do it. Let's see. The smart thing would be to convert it to something over 100. So that would be like dividing by 5 here and then dividing by 5 here. That would produce 100. This would give you a decimal, 62 divided by 5. 5 goes into that 1 time with 1 left over, 2. 2 left over is 4. So 12.4, I believe. If it's 0.124, all right, in the style of a percentage, it would be about, well, it would be exactly 12.4%. Let's see if I'm correct. All right. I'll enter 62 over 500. You can see what the reduced fraction is. Remember, you hit 62. Sorry, I'm holding too much stuff here. Hit ABC button here, the denominator of 500, and notice that it reduces nicely to 31 over 250, right? That would be the simplified fraction. What is it in the style of a decimal? The top divided by the bottom, whether you use the simplified fraction or not. Clear. 62 divided by 500 is, again, 0.124. Right? So uh, 0.124 would be about 12%. You know? So not too many people injured, you know. or well, it's unchanged in this case, so less harm done. Last one is people who had the increase. This is hurting people. It's just 59 over 500. And that is reduced as it can get. All right. If you were to convert this to a decimal, do that really quickly. 59 divided by 500 is 0.118. Alright, which again would be times 100. Move the decimal over, that's in the same instance here. Move the decimal over, and you'd get 11.8%. So just shy of 12%. Okay. They didn't ask you for anything but the actual fractions, so this is what you would have. Alright, 379 over 500, 62 over 500, and 59 over 500. Okay. Yeah. Alright, now let's go back and look at this sheet. Which is to delve into the differences between theoretical and experimental probability. A coin flip is a very good example. Let's see if I can reduce that. And I'll get rid of the gobbledygook here. Aside from having slightly tweaked different formulae, here's what results would be. To explain. All right, imagine a coin flip, hence the heading here, coin flip. And somebody tabulated the theoretical and the experimental probability results here. All right. If we were just purely doing this abstractly, a coin flip is pretty simple, right? It's the most basic probability experiment, right? And you did it 10 times, right? The probability of rolling a heads would be the number of event favorable to heads over the total possible outcomes in the set, in the space. Right? So whatever the number of tosses that you can conceive of would be the denominator, and whatever in theory would produce the top, all right, would be the numerator here. The heads would be the numerator. So in theory, all right, if you did 10 rolls, exactly 50% of the time, that's 5 out of 10, you would get, 5 heads and 5 tails, all right? If we're just examining heads, for example, that would just be 5, all right? What is that? It's a half. What is that? It's 50%, right? That's what theory predicts, right? And it's totally legit, right? If you just change the number of tosses, you went from 100, what you should get is exactly 50 heads. If you did it 1,000 times, then what you should get is exactly 500. That doesn't mean you're going to get them in a row, all right? But that's what, in theory, you should get, all right? In totality for heads, 500, exactly half, all right? 10,000, 5,000, 100,000, 50,000, all right? Then there's real life, all right? All right? The experimental probability. Somebody took the time to actually record the results of doing the experiment multiple times. Again, the formula would be almost identical. The probability of rolling heads, though, would be expressed as a frequency of heads over the number of trials, the number of games. So what's going to change is the denominator, just as in the last case, right? It'll start out being 10, But what you might see as a result of doing the actual game is that it's not 5. That it ends up just being dumb luck 4, right? So that means rather than 50%, it would be 4 out of 10, which is 40% of the time in real life. Now notice something. I'm going to put it here, all right? This is 40%. This is 45%. This is 54.6%. This is 48.52%. This is 49.770%. I'm just taking these, what would be the fractions empirically, converted to decimals as they're written, and then just going the whole 9 yards and writing them in the style of percentages. Because I think it's easier to talk to a person about that. Yeah, the decimals, technically. All right. In the first record here, number of choices 10. What actually showed up was 40% of the time, heads. All right. After 100 trials, what actually showed up was that heads occurred 45% of the time. Notice that it was a little bit more. All right. After 1,000 trials, it was more than 50%, 54.6. It exceeded the maximum of what you would presume would be the maximum of 50. After 10,000, it went to 48, so it's to fluctuate, right? 0.5, right? And after 100, imagine doing this coin flip 100,000 times. Oh God. You see that it is at the threshold, on the doorstep of what would be predicted. This is practically 50%, right? But you only observe that after doing something a lot, right? That's really what the whole point of this is, right? I took what I had mentioned earlier, the law of large numbers, and then included it from what was written on in your textbook here, down at the bottom, right? The law of large numbers states that the probability applied, the statements apply in practice to a large number of trials, not to a single trial. Right? It is the relative frequency over the long run that is accurately predictable, not individual events or precise totals. Meaning, over the long run, the empirical probability approaches the theoretical probability. That's really the essence of what you must know about the law of large numbers, right? In order for these things to match, you would have to do a lot of trials. The more, the merrier, okay? The theoretical will approach, the empirical will approach the theoretical. Okay, I like, not to pat myself too hard in the back here, I like my own sort of rephrasing of this. All right, this is on the other sheet. In practice, probability applies to a large number of games and not just one or a few. All right, meaning the empirical probability will approach the value predicted by the theoretical probability over the long run. It's the same thing, just rephrased. Empirical approaches theoretical. All right. Now, let's go back and look at number 5 from the examples. I thought that was a bit boring, so skip 4. Okay. All right, now this is again worthy of our time because not a lot of people, or not everyone, has ever actually played, believe it or not, with a deck of cards. Don't take for granted that people have had that pleasure. So we'll go through this problem as to get you build up some experience here. A standard deck of 52 playing cards, which again is the type that I had modeled earlier, is shown in the figure, which is below here. The deck consists of 4 suits: hearts, clubs, diamonds, spades. Right. Those are hearts, and diamonds are also red, if you're not familiar. Clubs Think of Lucky Charms and spades. Alright. So it looks like clovers, right? Each suit has 13 cards, including numbered cards ace, which stands for 1 through 10, and then 3 face cards, otherwise known as picture cards, right? The jack, the queen, and the king. Hearts and diamonds are red cards, clubs and spades are black cards. This is somebody attempting to explain what a deck of cards looks like, right? Which is never as much fun. Again, not to beat a dead horse, but in the position of teacher, one thing that you absolutely must do is be as lucid as possible. All right, so I'm just taking out the jokers there. All right, don't just talk at somebody. Give them actual visual aid. All right, it's very important. All right, this is what's being described. The 4 suits of cards, as you can see, diamonds, spades, hearts, clubs, and that some of them have pictures, jack, queen, king, and an ace stands for 1. All right, and there's 52 normally total, unless you're dealing with a pinochle deck or something like that. All right, anyhow, 1 card is to be selected at random from the deck of cards. Determine the probability that the card selected is situation 1, 2, 3, 4, 5, 6 here. All right, A through F. All right, we're doing theoretical probability again. So this is our formula. The probability of the event is equal to the number of events favorable to such and such over the total in this space, so set. All right, now, I'm gonna try to get away with chopping this up into part A, B, C, D, E, and F. Alright, and I'll do it each one. Alright, we're just doing one draw. Alright, the probability of drawing an 8. Right, you might write it like this, and I would take the time to do that. The probability of an 8 is equal to the number of events favorable to an 8, and say it to yourself as you're writing it, over the total number of outcomes in the set, or the sample space, or the space, whichever you prefer. Right? How many cards are there possible? Unique cards are there. All right. There's 52 described, so the number down here is going to be 52. All right. How many cards are labeled an 8? And bear in mind, they're not specifying the suit. So, if you dug through an actual deck of cards, human me, you would see that there's an 8 of diamonds. All right. And there's an 8 of clubs. And there's an 8 of spades, not in this order, right? And there's an 8 of hearts. All right. So, 4 suits, 4 different 8s. That means that the number of events favorable to the slightly less specific, slightly more general scenario of drawing an 8 is that it would be 4 cards. 4 out of 52. Right? Now, again, if it's possible, do try to reduce it to the simplest fraction. So 4 out of 52, divide each of these by 2. Well, 4 actually is the GCF. You would end up with 1 out of 13. Right? Which is what as a decimal? I'm just curious now. 12, something like that? No. 1 divided by 13 is, if you move the decimal over twice, about almost 8%, right? 7.6, right, and change. So just about 8%. Not that they asked. Okay. All right. Okay. All right. B. All right. Need a little extra extra room here. All right. The probability of not an 8. You could just say not 8 is equal to the favorable events favorable to not 8 over the total in the set. All right. What is the denominator going to be if you're talking about a 52 deck of 52 playing card deck? Well, it's going to be 52 again. So you still have 52 as a denominator. If you take into consideration that there are 4 cards that are labeled 8, you could spare yourself a little bit of trouble having done this problem already. It would be the total minus 4, right? Those things that are 8. And in which case you would have what? 48. Right. If you had 48 out of 52, and you simplified the fraction, sorry I'm scribbling on top of it, 48 divided by 4 is 12. And 52 divided by 4 is still 13. So 12 out of 13. Right, which is like 92% if you're curious, right? It's practically, you know, it's if you were going to bet on something, it's a whole other story. We'll talk about odds later, all right? But it's a good bet, all right? That you're not going to draw an 8. Right? Now, drawing a club. Again, try to be concise. All right? The probability of drawing a club, how appropriate that I have a black marker, would be equal to the number of things that are clubs, essentially, over the total in the set. That does not look right, but okay. It's like broccoli more than it looks like a suit of cards. It is described actually, you know, in the problem here. But if you took the time to dig through a deck and you counted all of those things that are labeled with a club, all right, you would see that there are in fact 13 of them. So this would be 13 out of 52, right, which is 1/4 simplified, or 25%. I'm going to need a little bit of extra space, so what I'm going to do is I'm going to erase what I have here and then just do the work for the last 3. Alright. Unless I can get away with this. Yeah. Let me do D here. And we'll try. I don't like to erase things because I think sometimes it's good to see the entire forest as a reference. We're up to D here. The probability of a jack or a queen or a king. That is a picture card. Maybe I should erase this. Yeah. Reluctantly, I will do that. Because this is a little bit more involved. Clarity is ultimately what you should err upon. Err on the side of caution, we say, well, err on the side of clarity. So if you have to erase something, do so. We're doing D here, all right? How many, if we're looking for the probability of a jack, I'm going to use a J for an abbreviation, or a queen, or a king. You could write it like that nicely. All right. That would be the number of things that are jacks or queens or kings out of the total. Right. Now, again, it's described, so even if you didn't have a deck of cards, how many jacks are there? There's 4, one of each suit. There's 4 queens, one of each suit, and there's 4 kings, one of each suit. So, not that it's super important, but notice that we use the word or here. That will be important later. If it's 4 plus 4 plus 4, that would make this 12 out of 52 again. If you simplified it, they're both divisible by 4, that's the GCF. We could use a calculator. That would be 3 out of 13. Which in the style of a percentage would be something like 23%. Probably the fraction again is what you expected and nothing else. Right? I just mentioned the percentages again because I think it makes things a little bit more intuitive. Right. A heart or a spade. Pardon me, a heart and a spade. There's a trick question, right? The probability of a heart, a blue heart here, and a spade. No, that's not a trick question. No, it is. Okay. There's this concept which I'm sort of dancing around called mutual exclusivity, which is not appropriate to mention right now, but that's where you have this issue. There's a formula basically when you have a situation like this that arises. Anyhow, because you have it described, because you may potentially have an actual deck of cards available to you, you could reason it through. All right. The probability of drawing a heart and a spade at the same time is equal to the number of events favorable to a heart and a spade out of the total in the set. Are cards ever hearts and spades simultaneously? Well, if you dig through, again, your deck of cards, you see that there are hearts, yes, and there are also spades, but they're not one and the same. They are separate from one another. So this is indeed a trick question, right? Can a heart be both a spade and a heart? Can a card be both a heart and a spade at the same time? No. So the number of events favorable to that situation would in fact be 0. Right? There are 52 cards, but regardless, this is a 0% chance of ever happening. One more of these, and then we'll move on. Okay, last one, F here. The probability of a card greater than 5 which you might write concisely as 5 is less than the card. The inequality symbol would be less than in this orientation. All right. And less than 9. So this is a situation described here symbolically. The card is less than 9, and it's greater than 5. If I'm talking about those two scenarios simultaneously, a very concisely written way of writing that would be like so, where you have the word card in between these inequalities oriented as such. The card is less than, is the point 9, but it is greater than 5. Right? So it's something between, right, essentially. But not including 5 and not including 9. They're non-inclusive, right? So what are the number of events favorable to this scenario? Less than 9, greater than 5, over the number in the set. All right. The bottom is super easy, right? Because we know, well, it's 52 deck, playing card deck. All right. So it's going to be 52 again. All right. But we have to consider a lot of things. All right. Things that are, we're not specifying suits here. All right. Let's figure out 1 and then maybe multiply by 4. The number will be times 4 for the 4 suits. All right. Now, again, it might be helpful with the visual aid. So it doesn't matter which set you use, but I'm going to go look at 12 here. clubs. All right. So ace is less than 5. All right. We need something essentially greater than 5. All right. So we're not going to have ace. We're not going to have 2. We're not going to have 3. We're not going to have 4. We're not going to have 5 itself. All right. What are cards that are greater than 5? 6 is greater than 5. All right. 7 is greater than 5. All right. 8 is greater than 5. And then technically 9 is greater than 5. But this is the other condition now. We want to make sure that the cards in general are in this realm here, between this limit and that limit. Right? So things that are 9 and beyond, we're excluding them. All right? We're not going to take 9, we're not going to take 10, jack, queen, or king. All right? How many cards are there that are in this spectrum? All right? The number 6, the number 7, and the number 8, regardless of suits. All right? I'm just using clubs because I like it. All right? So that's 3 of those. All right? So the number is, there are 3 cards in this spectrum. All right? If there's 4 suits, how many is that total? There are 12. Right? And then you would naturally reduce that, but just because I don't want to mess up my deck, I'm going to put this back first. All right. Being a twit right now, but humor me. Okay. So there are 12 total across the 4 suits out of 52. If you simplify this again, you would divide this by 4 and divide this by 4, and that would be a 3, and that would be a 13. 3 out of 13 is something like about 23%, if you're curious. 12 out of 52, 3 out of 13 is just simplified. Okay. Alright, now let me show you this sheet to summarize some information. It would be appropriate at this point. Facts about probability. Alright. You already have, in theory, a lot of experience with fractions and decimals and such. But this is a little bit of a reminder. So, to tie it all together, probability, I'm just abbreviating as prob, is mostly written in the style of a fraction. So as a model, you'd see something sitting on top of something else, right? You can, when it comes to probability at least, convert the probability to a percentage. Why? And why would you want to do that? Because it is a little bit more human. We are totally comfortable when people quote percentages to us, right? We somehow. And we go, all right, yeah, I kind of grasp what you're saying. If somebody said 50%, you go, all right, yeah. 50% of the time it could go either way, right? Here's that diagram from earlier in the semester, just as a little reminder. If you had to convert from a fraction to a percentage, you were starting at a fraction point, going arrow point, arrowhead here, to a percentage, you're multiplying by 100. Just remember that, right? If you like, right, you could convert it to a decimal first, right, which means you divide the top thing by the bottom to establish the decimal point, and then nonetheless, converting from whatever to a percentage, you multiply by 100, which has the effect of moving a decimal point twice toward the right. All right, now there are some other things to consider here, right? The minimum probability would be, in the style of a fraction, would be 0 over 1 technically. In the style of a percent is a 0%. What does that mean? It means that something is mathematically impossible of happening. All right. What is the maximum probability? The maximum would be 1 over 1, if you like it in the style of a fraction. which would translate to 100% chance, which means it's absolutely certain that something is going to happen. If on the weather report they say, yes, it's 100% chance of rain, then you stick your head outside, it's raining outside. Right? Unless they're just really bad at predicting. This is important, though, right, to bear in mind as far as the numbers involved. Right? Probability is non-negative. Right? Non-negative is a general way of saying not negative, but also it could be zero. Right? Because what are things that are not negative? Well, if the negatives are everything this way on a number line, then what are the things that are not negative? 0 and all of the positives, right? All right. So it's either going to be 0 or it'll be a positive fraction, essentially. Right? If you wanted to write that sort of concisely, all right, the probability would be written in between these inequality symbols. You don't have to do this, but it is a nice, concise way of talking about it. All right. The probability would either have to be greater than in this orientation, 0 point is facing the smaller thing, or equal to exactly 0. Or it would have to be less than 1 in this orientation. Point is facing the probability, or exactly equal to 1. Right? So it's something in between, and it includes 1 and 0 as possibilities. Right? It's inclusive. Right? Now, there are some other formulas here. The sum of all probabilities of a specific game or experiment would add up to 1, right? Remember, sum meaning adds up to 1, which means that even if you have several fractions, the maximum is still going to be 1. If you're talking about some specific situation, the probability of some specific event, let's just call it A, that would be a chunk of the whole, so some fraction of the total. And then if you're being more general about things that are not A, that would be the balance. Right? That would help you sum or add up to 1. Right? There's a fancy way of referring to that chunk that isn't what you want. It's called the complement, remember, from set theory, right? And that can be abbreviated like this, right? Remember, the complement is often indicated by a tick mark. The complement of A is not A, right? I wrote that here, right? If you were asked to figure out the complement, all right, using a formula, it would be this. It would be 1 minus whatever those things are that are A, right? The actual thing that is the thing. All right. Not A is 1 minus what is A. Okay. All right. Now, for the sake of timeliness, let me show you just one part of this example that I had from another book here. I like this problem because it's kind of fun because it's about candy, right? A 2-pound bag of Hershey's Miniatures candy contains 33 milk chocolate bars, 27 crackles, just like a crunch bar, all right, 26 Mr. Good bars, something with peanuts, and 19 special darks, which is the one that I like, all right? Anyhow, find the theoretical probability of these different situations. Because the complement formula is really the new concept, let me skip to that, right? If you wanted to figure out the theoretical probability of selecting specifically this, not a milk chocolate. All right, let me write that first. All right, the probability of not milk chocolate. I'm going to write that as concisely as possible. All right. That would be the number of events favorable to not milk chocolate over the number in the sample space or the set, again, whatever you prefer. Right? That's just taking the standard formula for theoretical probability and adapting it to this unique problem. All right? We can, if we want to, and I'll do it both ways, borrow the complement formula. Right. The probability of not A is equal to 1 minus things that are A. Right. The whole, essentially, minus the part. Okay? And in this scenario, that's, as long as you feel comfortable, that's probably the better way to go, because there's less math involved. You don't have to do a lot of work when you're figuring this out. So go ahead and use the adapted formula that you see at the top here. There's no sin in that. All right? But it might be a little extra work. All right. Now, one thing that we would have to figure out, and it's not explicitly stated, is that we would need to know the total number in the set, right, or in the sample space, to calculate this theoretical probability. How would we perhaps intuitively do that? Right? This is what each individual type of candy adds up to: 33, 27, 26, and 19 individually, right? But what would it be actually total? We would have to do that in any event, right? So go ahead and do it brute force, right? 7 and 3 is 10. 6 and 9 is 15. 15 plus another 10 is 25. So I'm going to carry the 2 here. All right. 2 and 3 is 5. 5 and 2 is 7. 7 and 2 is 9. 9 and 1 is another 10. So 105 pieces. 105 candies. All right, total. All right. That means that that's going to be the denominator. 105, right? Unless I miffed it. No, that looks correct. All right. Now, this is where it's really your choice to use the rest of this formula here or the adapted model. All right. If you're going to go with the original plan, which is the adapted formula, to figure out things that are not chocolate, milk chocolate that is, you have to consider, well, what are the things that are not milk chocolate? The crackles are not milk chocolate technically by name, all right? Mr. Goodbars and Special Dogs. So without it explicitly being stated, what you would have to do then is add up these things just by themselves. This totaled by itself, right? So if 6 and 9 is 15, and I'm taking advantage of commutative property, you see. 15 plus 7 would be 22, right? So that would be a 2, and I will carry it over 2, right? 2 and 2 is 4, 4 and 2 is 6, and 6 plus 1 is 7. So it would be 72 total in that case. Things not milk chocolate would be 72 over 105, which if you get, again, if you like, right, you can convert to a percentage. I'm going to take 72 and divide by 105, and you see that you get that as a decimal, 0.68 and change. All right, so that's about 69%, right, if I move the decimal over twice. 69% theoretical probability, right? Or you could try to simplify that, which I don't believe it is. 72 is divisible by 3. Actually, they're both divisible by 3. Right. So 72 would be what? 2 with 1 left over, 4. 3 goes into 10, 3 times 1 left over is 5. It would be 24 over 35 in theory. All right, let me just verify with the calculator. 72 ABC button here, and then put 105 underneath it, and it should simplify automatically. Yes, 24 out of 36, 35 rather. Sorry. All right. So this isn't in your book, but this is the answer. 72 out of 105, simplified 24 out of 35. Well, about 69% chance of things that are not milk chocolate if you just randomly stuck your hand in the bag. All right. Now, if this is the alternative, perhaps it is worthy of consideration because it might take up less time. All right. Meaning you wouldn't have to add these things if you knew this formula. The probability of not A, all right, which again, if you're curious, could be written as probability A complement, right? If you don't mind the tick mark to represent the concept of not, right? What you will have to do only in terms of a fraction is figure out, not that, but just the things that are relevant, the things that are milk chocolate, which means you'd be paying attention to just this 33 here, right? So by itself, this would be 33 out of 105. And then you would have to, you could either enter this into your calculator or figure out brute force, which is that's a good mental exercise. All right, 1 whole expressed in the amount would be 105 out of 105. Right? And what you know about fractions is that once they have common denominator, they would naturally, you just really have to pay attention to the top. So it's a matter of subtracting 105 minus 33. And you should get 72. 5 minus 3 is 2. That would be indeed 7. So the probability of not milk chocolate is again 72 out of 1 over 5. There's more than one way to do it, as that is often the case in math, right? So just beware. This is a good use of the formula. All right, now the last thing is just to talk about genetics a little bit, and then I'll stop here. All right. You might want to read about Gregor Mendel if you've never had a biology class. It's interesting. But let me show you something from personal experience and how it's relevant to us now. I had worked in Staten Island briefly, and while I was there, the vice principal shared with me something that was taught to her by another math teacher. Right? Anyhow, if you've ever taken a biology class, the subject of basic genetics comes up at some point, right? And what they usually do is draw this sort of window-shaped diagram, right? What I'm here to tell you is basically this, right? What is good for biology, the diagram, right, is also good for math, right? It's good for algebra. I think I may have touched upon this when we did 090 material. And you'll see that in terms of genetics and then in probability, right? So let me just remind you of this. Right? From the perspective of a math person, right? If you had this problem, x plus 2 times x plus 3, right? You may have some vague inkling about what you have to do just intuitively, especially if you've seen algebra, at least algebra 1 in high school perhaps, right? There's this concept of FOIL, right, which is an acronym for the instructions. You do the things that are first, meaning you cross the x's, f at first, and you get x squared, right? And then you do the outside things, which would be the x technically again, and then this 3 here, so I'm just connecting it with arcs here. See if this is better with a little bit of light. And then you combine them and you get positive 3x. And then you do the things that are on the inside, right, which is 2 times x, which would be positive 2x. And then lastly, you do the things that are last, right, happily. The 2 is last in this parentheses, and the 3 is last in this parentheses. I like to connect them with awks. So 2 times 3 would be 6, right? And what would you accomplish in a scenario like this? Well, you're eliminating the parentheses, really. And then if it's possible, blend together the things that are like terms, right? The things that are the same letter and technically the same degree can be added. That is just the coefficients, just the number sitting in front, namely the 3 and the 2. So what actually is 3 plus 2? 5, which would make this x squared plus 5x plus 6, right? Now, here's the interesting novel thing that was taught to me by a third party, right? If you are familiar with Punnett squares from biology class, what you can do is sort of write the first parentheses contents here is x plus 2 along the top, and the second parentheses is contents along the side here. Sort of as if they were mama, right, and papa, if you will. X plus 3. Right. And then you blend them together in a similar fashion, like a multiplication table, right? So it's kind of intuitive, right? If you're crossing these two things, what's the abbreviation for x times x? Would be x squared, right? X with an exponent of 2, because you add the exponents and you get a 2 when you multiply the bases. And then you write the result in the box, right? Then you do the same thing here. X times 2 is plus 2x, right? And then you do the same thing here. 3 times x is plus 3x. I like to put the signs too. And then lastly, 3 times 2 would be plus 6. And you see that you get the same results. Now, normally what happens is that the material left over here that is diagonal are the things that are the like terms. Check to see that they're the same letter, they're the same degree technically, and you get the same answer, right? You get x squared plus 5x, and then plus 6. Right. Same as before, doing it either the FOIL way or this sort of newfangled way, right? Punnett squares. All right. Well, this idea of a diagram comes from biology originally, right? And it has to do with predicting let's just say eye color as an example. Now, normally what happens is that instead of having an algebraic expression as your mama and your papa, is that you see the genetic alleles, I believe is the correct term, of each of the parents that are crossed, right? So there are dominant and recessive traits. I'm sure that actual genetics is more complicated than this, but capital B is what represents brown eyes. Brown, and that is dominant. All right? And lowercase b represents blue. All right? And it is what you would refer to as recessive, right? Not dominant. Right? Right. Now, let's suppose that you had parents that carried both of these genetic traits. Right? We could make a prediction about what perhaps their children's eye color would be. All right, so let's say that mama, who is written along the top here, is a hybrid person that has both the dominant trait and the recessive trait. That is, she has brown eyes, but she carries the blue gene, right? And papa, is similarly a hybrid person. So has brown eyes because that's dominant, but is carrying the recessive trait, lowercase b. Right? Let's see what would potentially happen. If you cross these, you just write them adjacent to one another. All right. In the first case, you have the possibility of an offspring that is purely brown-eyed. Right? They do not carry the recessive trait that is blue at all. Right? And if you cross in these two genes here, B and lowercase b, what you would end up with is what is technically referred to as a hybrid, I believe. Right? And then that would happen again here. Right. There is one scenario, though, where if you crossed this genetic trait with this one, that you would have a child, right? Potentially, not technically for sure, that is purely blue-eyed. Right? This is purely blue, right? Because it doesn't carry anything but the recessive trait. Right? And this is purely brown, because it only carries the dominant traits. Right? What should happen in theory is that even if you ended up with a hybrid offspring, that they would still nonetheless produce brown eyes. Now we know that there are green eyes and there are hazel eyes and there are other situations, but in this theoretical scenario, for the sake of simplicity, let's just assume these are the only two choices. All right, this person in theory would be brown, and this person would be brown as well. All right. Now the important thing to remember is that this isn't necessarily what is actually going to happen. It's just theoretical probability. All right. But what we're doing is we're going to describe using Punnett squares, all right, theoretical probability. Ability. All right. All right. Remember, I really have to emphasize that. This describes, using Punnett squares, theoretical probability. Right? Theoretical probability isn't what happens necessarily. Right? Experimental probability, which is to produce offspring, it's so cold to think about it that way, right? Would be the actual reality, right? Theoretical probability isn't what happens necessarily, but would be in the long run. All right, now, in other words, two people that marry and have children, all right, aren't going to necessarily have 4 kids exactly, right? But this would give you some idea, right, theoretically about what is possible, all right? There is, if you think about it, not that this is a good thing or a bad thing, the probability of this recessive situation would be the number of events favorable to that recessive situation over the total in the set. 4 is just the convenient denominator here. How many situations are pure recessive BB, lowercase, lowercase? Right? 1/4. That means 25% chance. Or to put it in the context of the I column, there would be a 25% chance if you had 2 hybrid people to begin with produce, while in the process of producing offspring, that one of them would be purely blue-eyed. Right? Blue eyes, apparently, at least according to the story I was told, only happens when you have both parents carrying the recessive trait. right? Because it is normally dominated by brown genetic trait. Okay, so that's kind of interesting, right? Even though this person, the child produced, the offspring produced would be a hybrid themselves from having two hybrid parents here and here, they still, in theory, should have visibly brown eyes, right? Without taking green or hazel or gray even or pink into consideration, because that is possible in real life. All right. What is interesting though is that of these, the probability of brown, if you will, is taken into consideration. That would be the number of events favorable to brown out of the number in the total sample space, which would be how many? 3 out of 4, right? That doesn't mean that a person is going to have 3 kids and it's guaranteed that they're going to have brown eyes. But there is a greater likelihood, right, that if you just do this experiment that many times, that it's 75% chance. Okay? All right. If you had the energy to have 100 children, all right, the experimental probability and the theoretical probability would approach one another. Well, the experimental would approach the theoretical, right? Anyhow, 3 out of 4 produces a 75% chance of brown eyes, and 1 out of 4 describes a 25% chance of blue eyes, right? Given that mama and that papa, hybrid brown. Okay. Anyhow, I probably sorted that, but let me just remind you of a couple of things and we're done. Okay. I'll turn this off now. For homework, all right, please do section 11.1 in my lab. All right, that's that. Okay, and then I'll just see you again on Thursday. All right, we'll do 11.2. All right, remember next week is Thanksgiving, so if you haven't, probably a good idea to get your turkey now. All right, please don't wait for too long to start this, because especially chapter 9, all right, that is a little too alien. I would advise anyone to just wait too long. Anyhow, we're in the whole of the ball game now. We're talking about probabilities, so again, don't let it get ahead of you. All right, thank you guys for sticking with me. I will see you again on Thursday. Be careful out there.